Welcome to a lesson with Dr. Powell. Let's take a look at how to find the limit of a sequence that is defined just formulaically, such as a sub n is equal to maybe something like 1 minus 2 to the negative n, something like this. This is nothing more than just realizing that this actually is a function, where n is an input and a sub n is the output. And we're only looking at certain domain points. Yet, if you have any function at all, such as this one, and you're just looking at certain domain points, so just take different points on it, and the function itself has a limit, don't those points also go to that limit itself as well? So you could just imagine this as being something like this. F of x is equal to 1 minus 2 to the negative x. Then we're just taking a limit. This is an exponential function that represents decay, and it decays to 0 as x goes to infinity. So the limit of this part is just 0, whereas this is just stabilizes at 1. So the limit of this is simply 1. So, and that's the same as the limit of the sequence as n approaches infinity, a sub n, that's simply going to be equal to 1. So this is just an example. We can also look at things like this. What if we had something like this? What if we had the sine of n, say, all over n squared plus 3, and this is added to something else, added to maybe like 5, and we know this is a sequence here. You might say, well, this sequence wobbles around, especially with this sine of n. It's going to cause some bounciness in here. However, the bounciness is negligible to the denominator, and you can even think of bounding this sequence above and below. We know the sine of n is bounded above by 1, bounded below by negative 1. So this sequence, the terms of it would be bounded below by negative 1 over n squared plus 3 plus 5, bounded above by 1 over n squared plus 3 plus 5. And in both cases, as n goes off to infinity, this goes to 0, this goes to 0, which means this sandwich in between will go to 5, since this part goes to 5 and this part goes to 5. So we know that the limit as n approaches infinity of a sub n is simply equal to 5. So what we're doing overall is we're just using the fact that we can think of this n as even being a continuous variable and simply just take a limit. The same limit types of properties hold, and we can still combat it in that way. Here's another example. Let's suppose that we have something like a sub n is equal to the square root, say, of let's do n to the 4th plus n minus 1 all over, and then let's do 5 n to the 4th plus 2. Okay, suppose we have something like this, and we want to be able to find what the limit as n approaches infinity of a sub n is. Well, we use limit properties. Think of this as a function. You're just taking a limit of it as n goes to infinity. Square root is continuous. The limit can pop inside the square root. Then we're looking at this part. Now we can use the fact that we can divide top and bottom by the same thing and have an equivalent fraction and have the same limit. So, so if we divide top and bottom by the same thing, because when we do that, we're multiplying by something, which has a limit of 1 as n goes to infinity. So that's perfectly fine to do that, to write down an equivalent fraction here when we're computing a limit. Divide top and bottom by n to the 4th. How does that help? Well, that gives us a constant and gives us fractions which go to 0. So divide the top by n to the 4th, we would have a 1 plus 1 over n cubed minus 1 over n to the 4th. On the bottom, we would have 5 plus 2 over n to the 4th. We divided top and bottom by n to the 4th. Okay, then when we take a limit, these parts just go to 0 as n goes off to infinity. So we're left with, but then remember the limit's under the square root. So we're left with the square root of 1/5 as our limit. This is using algebraic properties. Thanks for watching.